Okay, so let's talk about accelerated motion. So just a reminder, we generated this graph by sending a little cart down a track, okay? So what that means is, if we imagine this is the track, what we did was we put a little sensor, basically an electric eye, over here, okay? Here's my electric eye. How do I know it's electric? Because it's got a cord plugged in the back of it, right there, okay? This electric eye is able to watch and tell you the position of an object on the track. So what we did was we took a little cart on wheels, and we put the little cart up at the top of the track like so. All right, there it is. Has little low friction wheels on it, and we released the cart. And the cart began to move here, okay? And what the electric eye and the software was able to do was it was able to track this as position versus time. Okay, so P versus T, position versus time. And the graph it generated is as so. Now, unfortunately, I cut off the time, but I think these were 1 second intervals, okay? So for this moment of time, I can't remember. It doesn't really matter that much. What's important is that we relate what happened here to what we see here, okay? So from the perspective of the eye, the object is starting far away from it here. There's its, if you want, initial position. And I grabbed it just before it crashed into the eye, and so its final position is here. How far did the object travel during its motion? Well, I don't know, what's this? 1, 2, 3, 4, 5. So, I mean, this is probably like 0. 0.5. Ooh, that's hard to see, eh? 0. Oh, no. Less than that. 0. Let's say 1. It's probably 0.1. Or even less than 0.1. 2, 3, 4, 5. About 0.1. Okay? That was its initial, or sorry, its final position. 0.1, or about 10 centimeters away. Okay, so it stopped about 10 centimeters away, and it started just over a meter away at about 1.1 meters. So it went approximately 1 meter. Okay, so the distance that it covered was 1 meter. Okay, or if you want displacement was 1 meter. Would the electric eye consider this to be a negative or a positive displacement change? Negative or positive displacement change? Well, just look at what we have on the screen right now. Okay, you think it's positive? Well, how about we actually check? Because we can use math to check this. Remember, delta D is equal to final position minus initial position. Okay? It's a little bit hard to see, so let's use a dark color. So in this case, final position is 0.1 meters, and initial position was 1.1 meters. So what value do we get here? Negative 1 meter. So is it a negative or positive position change? Well, it's a negative position change. And if you look at this axis over here, which is your position, and you can just kind of make it out there, but it's your position axis, your y-axis, it starts at 1.1 and it ends at 0.1. So it's fairly obvious that the displacement change is in the negative direction. So it's a negative displacement change, okay? That's part A of this. It is no longer uniform motion. If the motion were uniform, what type of slope would we expect to see on a graph like this? What would it be like if we had constant velocity the whole time? Yes. Good. So we would go from not moving to here in a straight line. Well, clearly that is not the type of motion that we had. Okay. Just do a little recall right here. If we look at this slope here, okay, what we have on the slope is we have the rise. Start using colors we can see. We have the rise, which is negative, versus the run, which is positive. And if we had this motion, we would have a negative constant velocity. How do I know it's constant? Because the slope of this never changes. How much rise we have for a given amount of run stays the same the whole time. Is that the case for a line with a curve on it? No. Okay. And one way to look at that, oh, I can't erase these things? One way to look at that is to imagine that the slope, and I'll get there in a second, is a collection of individual miniature slopes, right? So instead of having one constant slope, you can look at it as being a whole collection of little miniature individual slopes. So right here, there's your slope. What's the slope on that? Zero slope. Zero motion, zero slope. Then here, then here, we have a slope kind of like that, right? So there's a little point here where the slope's about like that. Then a little bit later, the slope's more like this, right? So over here. So here's some points that we're sort of looking at. Here it's at, oh man, I'm used to printing on the dark color. Here we've got zero velocity, v equals 0. Why? Because it's going no meters every second. There's no meter change every second. Here, we could probably figure out what this is. We're not going to right now, but it's something higher than 0. And here it's even higher than that. And if we continue this trend, eventually we get to a pretty, I'll make it better with the straight line. We get to a pretty high velocity down here. That looks like, oops, that's probably a little bit much. I think I can correct that though. It's kind of like this, right? Stretch that guy out. Put her there. So now what we could do, right? Something that we could do is we could come along with our ability to find slope, and we could use our rise over run on each of these, right? So here's a rise, here's a run. Okay, leaves a better color, I think. Here's a rise and here's a run. Notice, low rise for long run, low rise for long run. Rise is change in displacement, run is time. Little change in displacement for long time means low velocity. Here, okay, more rise for, roughly the same amount of run. In fact, we actually just copy that and move it in here. So here's the run, the same as the run that we had before. And now we can't even make a rise that's close to that. We gotta come over here. Okay, I'd have to extend this line way up here. You'd see this amount of rise for that same amount of run. And you see what's happening here is we're getting more and more rise for the amount of run that we have. In other words, the displacement change is getting higher and higher and higher. So what we're tracking here by drawing all these little slopes is we're tracking the change in velocity as time goes by. This is an example of accelerated motion. Okay. What is the sign again of velocity in all of these cases? Is velocity, remember, the velocity is going to be told to us by the slopes on these lines. Is the velocity negative or is it positive in all of these cases? Negative velocity. Now, we have a negative velocity and that velocity is increasing. Right? The actual magnitude of the velocity is getting larger. Velocity is increasing. So the question is this an example of a negative acceleration or a positive acceleration? Okay, so velocity is increasing. Now, the question is acceleration in this case a positive or a negative acceleration? What is acceleration, positive or negative? You think it's positive. This is something that students have trouble with. The velocity, young man, is getting higher. Okay? The object is clearly speeding up. However, it is speeding up in the negative direction. So students often have a tough time deciding, the velocity is getting higher. Is that a positive acceleration or a negative acceleration? And here's how you look at it. So to make something accelerate, think about this. To make an object accelerate, what do we have to do to it? What do you have to do to it? Well, we have to kind of apply some kind of push or pull on it, don't we? In the case of an object on a ramp, you should be writing this down. In the case of an object on the ramp, the push on the object is coming from gravity. Okay, so to make an object accelerate, we need to push or pull it, right? You can think of it. You can think of a little kid, right, pushing a wagon or something. If the wagon has a velocity of 0, the only way to get that wagon going is to pull it. You got to pull it to make it accelerate. So there's a tie-in between pulling something and whether it's going to accelerate or not. Okay. So in cases of our object traveling down the ramp towards the electric eye, gravity is essentially doing the pulling. Okay. And as I continue to pull, my velocity gets larger, but it gets larger in a negative direction. So a good way, something that helps me to think about these things is think of accelerations as pushes and pulls, or as being caused by pushes and pulls. Okay? In fact, you can't make an object accelerate unless you push or pull it. So let's think about the scenario that we had, okay? So from the point of view of the electric eye, that object was moving in the negative direction, okay? So I'm going to draw a little number line, and we're going to think about an object moving in the negative direction along a number line. So if we have a number line, okay, in the case of this object, okay, we had the electric eye as the origin, and we started somewhere off to the right side of it, okay, from this perspective that we're talking about. The eye can only detect what's, how far away something is from it. So we're kind of like turning this view on its side, but just, bear with me and let's think about what that we saw happening. Okay? So here's our ramp. Here's our ramp, and actually to make it seem more like a ramp, let's make it look ramp-like. Okay? Let's just get rid of all of these and redraw them. Sorry. Sometimes I get going on this thing and then I don't do the best job of drawing what I want. Okay, so there's our ramp. Here's our object, and let's just say it's a ball. This ball is going to roll towards this side. Okay, so right now our velocity equals 0. Okay. When the ball gets down here, our velocity equals some value that is larger than 0. Right? Larger than 0 in the left direction. Okay? So in order to make something go from 0 to some high value in the left direction, how must we have been pushing on it or pulling on it? Well, we must have been pushing or pulling in this direction. Pushing or pulling in this direction, and therefore the acceleration is in that direction. Now look at these arrows. Look at all these arrows. Okay? We have velocity in this direction. Is that left or right? Left. And in physics, left is a negative direction. We have our push or pull in the left direction. We'll call that F, because we'll call it F later. That's negative. And we therefore have our acceleration in the negative direction. Everything is negative. If you have a velocity to the left, and you have a push or pull on the object that is also to the left, the object will speed up to the left. Does that make sense? Okay, sweet. If you flip it around and you do everything the same, but you do it to the right, okay, if you do it to the right, well, oops, if you do it to the right, back to this, okay, and you let the ball go, well, now you have a velocity that's 0 here, a velocity that's something larger than 0 over here, okay. The object has sped up to the right, therefore the push on the object must be to the right, and therefore the acceleration on the object must be to the right. So we've just learned something. Pushing or pulling in the direction the object is moving causes it to speed up, causes it to accelerate. Well, careful. I shouldn't be careful with that. It causes it to speed up, because there's such a thing as a negative acceleration. We'll look at that in just a second. Okay? So pushing in the direction of motion causes a speed up. Okay? So I just want to lay that out really simply. A negative acceleration can cause an object to speed up if velocity is already negative. If velocity is already positive, a positive acceleration can cause an object to speed up. If we imagine that we take pictures at equal intervals, what we would see is at the beginning, we would see quite a small difference between these objects, and we would see that that would increase as we went, right? So this is oftentimes how it's illustrated in books that an acceleration is happening. What they'll do is they'll increase the distance in each drawing between these objects and say, okay, each one of these pictures happens at the same time interval, kind of like a strobe light, and we see that the amount of displacement between each ball increases each time, okay? So that's a way to indicate that you have an acceleration, off to the right. So, can a positive acceleration cause an object to slow down? Can a positive acceleration cause an object to slow down? I hope that you're answering yes, it can. But let's see how that would potentially work. Let's say we have a slope like this. And let's say we have a ball starting, let's say we have a ball starting down here. Okay? And let's say that the ball initially has some high velocity. V equals something much larger than 0. Okay, what will happen is the ball will move up, but because it's going up a ramp, what you'll find is it's going to slow down, and eventually, if the ramp's long enough, its velocity will come to a value of 0. Are you with me? In this case, we have a negative velocity, the object's moving to the left, but the push on the object is to the right. The acceleration on the object must also be to the right. So look, negative velocity, positive acceleration means slowing down. So a positive acceleration absolutely can cause an object to slow down. That's how. Okay? And last but not least, just take this concept and flip it around this way. If we have an object with a positive velocity, okay, that is, we roll a ball up a hill. When we start rolling it, velocity is larger than 0. It's also positive because the object's moving in the rightward direction from our observation point. Sometime later, the velocity will equal 0. If that's happening, the push on the object is down the slope, because it always is. The push is always down the slope. And if a push and acceleration are going to be equal in terms of their sign, okay, what we have here is we have a positive acceleration, or sorry, I should say a positive velocity, and we have a negative acceleration or a negative push on the object. And what conclusion can we come to when velocity and acceleration are opposite each other? What happens to objects if their accelerations and velocities are opposite? Good. If accelerations and velocities have opposite signs, you slow down. Okay. Okay. So we generated ourselves one more graph here. And where this came from is what we did was we took the same setup we had before with the electric eye, but we did this with it. So there's our slope. So what we did here was we took our object, it's actually a little cart, but imagine that the electric eye is here, down here. Okay, and it's watching the cart this way. So we took this cart, which is, we'll just use a ball, and I gave it a push. Okay, so at first it was sitting still. You can see that here. It was sitting still. I gave it a push, and it had a high velocity to begin with. Velocity was greater than 0. It went up the plane, but it was slowing down the whole time. You can see how it was slowing down because look at the slope of the graph. Eventually, it slowed down enough that it stopped at its highest motion. It stopped, for a split second. But remember, the whole time, the force is acting on it this way, or the push is acting on it this way, so the acceleration is this way. So as it's moving up, take a look, its velocity is positive, but slowing down, right? So v equals positive. Up until this point, velocity is always away, or if you want, to the right, okay? Then at this point over here, velocity equals negative. The acceleration of this object always stays the same. The slope of the ramp stays the same, acceleration is the same. So the same acceleration the whole time makes this happen. We have a negative, so we have a positive velocity here. We have v equals 0 up here. And over here on this side, we have a negative velocity, okay? If we have a negative acceleration, this is where slowing down happens. And then here's where speeding up happens. Okay? And we'll leave it there. And next time we'll look at a velocity time graph.